Gravitational potential and gravitational potential energy, are they the same thing? What is the difference? Why gravitational potential energy is negative? Could it be positive? Why these two terms are so closely related to each other? In this video, I'm going to explain this very known yet some unknown concept, and I'm going to show you with some very simple equations how you can prove that gravitational potential energy is negative. We are also going to learn these two concepts deeply and look at some of the very important aspects. My name is Shaunak and you're watching this video on my channel Physics for Students. First, let us look what are the topics that we would be covering today. So we will understand what is gravitational potential first. Then we will look into what is gravitational potential energy. Then we will look into a mathematical definition. We will also see why gravitational potential energy is negative and how we can prove this concept through some simple examples. The viewers and subscribers of this channel might know that I have earlier 2 years back done a video on why gravitational potential energy is negative. You can see that it has reached more than almost close to about 5,000 views, but I am not satisfied with this 2 years old video. I'm not saying that it is wrong, but I always see there is an option, there is a provision to improve on certain concepts. So what I'm doing is that I'm elaborating this concept of GPE and I'm trying to improve on my earlier video. So first what we would look is that let us understand these two concepts clearly. What is gravitational potential and what is gravitational potential energy? These two terms seems to be very closely related to each other, but first we would look into a very simple layman's understanding of these two concepts. So you see, gravitational potential energy is always related to some kind of a work which is done. And gravitational potential is also something which is related to work done. This is some kind of a similarity which these two concepts have. Now let me show you a simple illustration. Now say for example, this is a gravitational field and here is a body. It can be a brick, a ball, anything. And there is another body which is located quite far, almost as infinity. Now if I am trying to bring this blue body so closely each to this body which is surrounded by a gravitational field, then we say that the amount of work done in bringing the body from infinity to that point is called gravitational potential energy. So you understand that it requires a huge amount of work because I have to bring that body which is far away located almost to infinity close to this body which is surrounded by a gravitational field. So in layman's work we can say that when we are trying to bring a body from infinity to that point, that is the amount of work done and that is gravitational potential energy. Now we take the same kind of a concept. There is a body which is surrounded by a gravitational field and there is another body which is located far away from this and it is almost at infinity, and we are also trying to bring the same body close to this body. But there is a difference. As you see, the definition tells the amount of work done in bringing the body of unit mass from infinity to that point. That means both of them are related to work done, but gravitational potential relates to something which is called unit mass, and gravitational potential energy does not include a unit mass, just the body which is being brought from infinity to that point. Now this shows actually the basic layman definition of gravitational potential and gravitational potential energy. But before we go into the mathematical definition, we will still try to look a little bit deeper. So the basic definition says that the gravitational potential at a point in space is equal to the work or energy transferred per unit mass that would be needed to move one object from a fixed reference point. That means the most important key point is that it deals with per unit mass. Now it is also similar to what we call electric potential, which is defined as the amount of work or energy needed to move a unit electric charge from a reference point to the specific point in an electric field. Only this deals with electric field and the above definition deals with gravitational field. But still there is a similarity. I just thought that this would bring interest to you. So this is the basic similarity between that. Now what is gravitational potential energy? It is the potential energy a massive object has in relation to another massive object due to gravity. So you see there is a relation between two bodies, one massive object in relation to another massive object. It is the potential energy associated with the gravitational field which is released, or in due course of time we will see converted into kinetic energy when the object fall towards each other. Gravitational potential increases when two objects are brought further apart, because due to the inverse square law of Newton's gravitational law. Now that we have seen the basic definition between gravitational potential, electric potential, gravitational potential energy, do you know that what is actually the similarity between gravitational potential and electric potential? We will see in this part of our video. So you see that gravitational potential and gravitational potential, I would say the gravitational potential at a location is the gravitational potential energy at that location per unit mass. So it is called V equals to work upon mass, which is denoted by UIM. Now it is analogous to the electric potential with mass playing the role of energy. So the electric potential is defined as the amount of work energy needed to move a unit electric charge from a reference point to the specific point, which is denoted equals to V equals to K upon QR, where K is the Coulomb's constant. Now you see electric potential energy works much the same way. That is, the charge which takes place is the electrical potential energy, but it is on the electric field instead of gravitational field. Now by virtue of its position in an electric field, a charge has an electric potential charge, which is just mentioned on your screen. If this charge is free to move, the force due to electric field causes it to accelerate, so its potential energy is converted into kinetic energy, just like a mass that falls in a gravitational field. So you understand that this kinetic energy can be used to do work. The electric potential energy is the work that a charge can do by virtue of its position in the electric field, and this does in case of a gravitational field. And gravitational potential energy is similar, U equals to minus G mmr, where capital M and M are the masses of two particles and R is the distance between them, and the capital G is a good old Newton's constant. Now this is something important. The force that produced by gravitational field is always attractive, but electric potential field has both the properties of being attractive and repulsive. This is a kind of a difference. So here you see the analogy between gravitational potential energy and electrical potential energy is given by this figure. So on the left you see the ball Earth system gains gravitational potential energy when the ball is higher in Earth's gravitational field, whereas here on the right hand side of the figure you see the two charge system gains electric potential when the positive charge is further away from the negative charge. So this is a kind of a basic analogy between gravitational potential and electric potential, so that you can understand that there is a similarity. Only the difference is that there is a gravitational field and here we do with electric field. Now, as you understand, as a physicist and mathematician, a layman's definition certainly doesn't work out. So in the next part of the video, we will look a little bit more into the mathematical definition one by one, starting first with gravitational potential. So what is the mathematical definition? We have seen that gravitational potential is basically the amount of work done in bringing a unit mass from infinity to that point. And it is called V equals to U upon M. And the unit is joules per kg. Okay. Now if I take a kind of a circle, say for example, I take the Earth right at a point O, and I draw a straight line which is up to infinity, and the distance from O up to P is R. Right, and the distance from from the center of the earth, that is O, up till A, where is the next point I'm trying to bring from infinity to A, is x, and I measure at unit mass, that is mass equals to 1. Now what I do is that I'm trying to find out the gravitational force on a body of unit mass at point A. That means what we will do, we will just plug in the values of Newton's constant, and here I have used x squared because the distance from O to A is x. So what I do, I plug in this mass m and we get F equals to gm upon x squared. So now what we do is that now that we have moved from point A, what I'm trying to do is that I'm mentioning another point B. Okay, and I'm mentioning the distance between A to B as dx. So we are trying to find out the work done in moving the body from A to B. We found out from 0 to O to A. Now I'm finding out from A to B. Let me go back and just quickly see over. That was, yes, on the point mass A. So here we are trying to find out from A to B. We know that work done dW, that is the small amount of work which is done, equals to F times dx, that is force times the displacement. So here F dx equals to gm upon x squared dx, and we know that force is basically gm upon x squared. So what we do is that we get the value gm upon x squared dx, because I just substituted gm dx squared in case of force, and dx is just as it is. Now the total work in moving the body from infinity, you see, from infinity to point P, is what I do a kind of a simple calculus integration. So the work done is equal to, from which point? From infinity I'm bringing it to point R. Right? So because from infinity to point P the distance is R, so I'm just integrating as gm x squared dx, and here I just put the 2 up on the upstairs, and you see the simple integration has been solved, and what I get is w equals to minus gm 1 upon x r to infinity, and on solving we get this 1 upon infinity will always be 0. So what I get is w equals to, we denote it by vp, equals to minus gmr. In general, this leads to something unknown, v equals to u upon m, which leads equal to v equal to minus gmr. So this is just to show you that work done in moving the body from A to B, right, and the total work done in moving the body from infinity to point P is basically the distance from 0 to P, and then I integrate it and I get something like minus gm. Okay, now this is done with gravitational potential. That means with a unit mass, right? We put it m equal to 1. Now we are coming to gravitational potential energy. So the figure on the right hand side will be the same, right? I just showed you what is the basic definition of gravitational potential, and I'm trying to find the mathematical definition of another body from infinity to that point. So the gravitational force on body from unit mass to point A, what would be that? It would be F equals to gmm upon x squared. We are not putting m equals to 1, right? Here you see I'm not putting m equals to 1. So what is the work done from point A to B? Again the distance will be dx, so work done will be F dx equals to gmm. Now you see here we are not putting m equals to 1, we are just substituting it as m, and the total work in moving the body from infinity to point B will be w equals to integrating from limit from r to infinity gmm dx by x squared. Only thing to notice is that we are not putting m equals to 1. Okay, so we solve this integration, we get this one. Obviously x goes upstairs, and what we get 1 upon x, and we get this one. Again this goes to 0, so we get w equals to gmmr. Now this is something which is quite noteworthy. So I just substituted w with u because most of the literature in internet and books shows u. So you see that this is basically the gravitational potential energy, which is negative. We will see further, but this is just to show you, derive that how gravitational potential is negative. Now important point is that you see that earlier we have found gravitational potential, which is u equals to vp. Now this m, if it is multiplied, this one, the earlier this is green, right? W equals to vp. Now this m, if it is put in here, what we get is this. So the gravitational potential, which was calculated earlier, when multiplied by mass, that is m, gives gravitational potential energy. So kind of a very simple, you can take a snapshot of this screen and you can understand this is how we derived and found out gravitational potential energy and how it comes to negative. But the question is that still we will need to find out that why gravitational potential energy is negative. I mean to see, there should be a mathematical derivation or a reason. So in this part of the video we will explain to you that why gravitational potential energy is negative. Okay, so first we will take the Earth's surface and there is a ball or a body over here, right? Now, according to the law of conservation of energy, what we know, the total energy of an isolated system remains constant. So what do I mean by that? That means on the surface of the Earth, total energy will be constant. What is total energy? Kinetic energy plus potential energy. Obviously, it will be constant. Now, we can also tell that kinetic energy is at an initial state and potential energy is an initial state, right? And it will also be constant. Now, if I take the surface of the Earth and I throw the ball or throw the body and it gains a height h. So, as the object gains height, what will happen is that the total energy always be constant, but kinetic energy plus potential energy will also be constant. And we will find the kinetic energy at the final stage plus potential energy at the final stage will also be constant. Now see, the thing is that on the surface of the Earth, when I have not thrown the ball, there is an initial position, that is Ki plus Pi, that is kinetic and potential energy both have an initial stage. As soon as it gains height, it gains a final stage. Okay, we'll further see now what happens. So we take those equations, and because constant minus constants, it cancels out. So what is kinetic energy final minus kinetic energy initial? That is the change in the kinetic energy. And similarly, we see that in potential energy, final minus initial is the change in potential energy. Okay, so what we can say, because the law of conservation, this constant cancels out, delta K, that is the change in kinetic energy plus change in potential energy equals to 0. So the law of conservation is not violated. Okay, now we know, I think you all know, by work energy theorem, we know that W net, that is the work done, is delta K. In simple way, we can say that the work done is equals to half mv square, kinetic energy at the final stage minus kinetic energy at the initial stage. Both of these can be called as delta K. Delta K means what? Delta K means the change in the kinetic energy from initial to final. Now you see what happens if I take this kind of a shape, right? Now you see when the ball stays at the Earth's level, I am saying that it is not being moved, then we know this as a potential is equals to mgh. But what is the height? The height is 0. That means potential energy leads to 0, right? And we can say work, that is W, equals to delta K, and this delta K is this one, that is the change of kinetic energy from initial to final stage. So the ball or the body stating at 0 has got h is equal to 0, so potential energy is 0. I think till now things are quite clear. Now if I take the same kind of a shape, right, where the ball, I mean to say illustration where the ball has gone up. Here you see this animation shows that the ball is being thrown up. So what we see from here is that as the ball is being thrown up, I mean to say when you throw things up, the speed slowly starts to slow down. So the kinetic energy, which is half mv squared, at one point of time, the speed or whatever the velocity you call becomes 0. So half multiplied by 0 equal to 0. So the kinetic energy becomes 0. Now when the ball is at the ground stage, you remember it has no potential energy, but it has got an initial kinetic energy. Now what happens as the ball starts to move upwards? So the speed slowly starts to slow down, as I have shown, v equals to 0, and gravity actually starts working. So what is the work done? The work done is basically the gravity. Now you see this same kind of an illustration. When the ball has been thrown up, it has got a potential energy, right? But it has no kinetic energy because the kinetic energy at one point starts to slow down and becomes 0. So what is actually happening? What is doing the work? The gravity is doing the work. So here you see the gravity is trying to pull things down. So the gravity starts pulling things down, and this work, that is the change in the kinetic energy, is nothing but the work which is being done by gravity. So at the initial stage, it has got no potential energy. We throw the ball upwards, the speed starts to slow down, the kinetic energy becomes zero, and it has got a potential energy. What is the change in kinetic energy is that as soon as we throw the ball, the gravity starts to pull down and it starts falling downwards. Okay, so from the last equation we got total change in kinetic energy plus change in potential energy equal to 0. So by doing simple algebra we get this, and we know W is equal to delta of K. So if we substitute delta K as W, we get W is equal to minus delta P, and from there we put the either side and we get delta P equals to 0. So this actually proves that gravitational potential energy has to be negative. Right, the gravitational potential energy is the work which has been done in order to pull that body in from infinity to that point has to be negative. The question is that still we are not convinced. We want to show certain example or single specific example which will lay out the foundation more strongly that can be it that using an example gravitational potential energy is negative. So we will see an example. So what we need to prove, let us go back to the earlier side. So what we saw is delta P equals to minus W, and here we also got delta P equals to minus W. We need to prove. Now we know that total energy equals to constant. Very simple, right? On the surface of the earth, when the body is at this stage, we say that kinetic energy initial plus potential energy initial equal to constant, right? So if it is U, I mean to say the initial state, there is an initial kinetic energy, suppose, right? But it has got no potential energy, obviously, because the ball has gained no height. Now, if I say that kinetic energy, it has got some kinetic energy, but potential energy is 0. So Ki plus 0 equal to constant. Now, when the body gains height, now here you see I have shown on the right hand side that there is a potential energy due to height. Right, and there is no kinetic energy because, as I told, that the velocity becomes 0, and at one point of time the kinetic energy is 0. So taking this analogy, we can say that the final plus potential energy is constant, but here because kinetic energy becomes 0, we can say the potential energy is something like Pf. So what we get, two equations, Ki plus 0 equals to constant, that is when the ball is at the surface, there has got some kinetic energy but no potential energy. When the ball is thrown upward, the second equation shows that the kinetic energy becomes 0 because it has lost the energy, but there is a potential energy due to height. Now we will take this equation, and what we will do is that 0 cancels out, so we will be kinetic energy equal to potential energy. Now suppose I take kinetic energy equals to potential initial equals to final equal to 20 joules. Now we need to prove that delta P equals to minus W, so we will take this part away, and what we are going to do is that we know that the change in potential energy is what? That is final minus initial. So, and what is final minus initial? That is the 20 joules. So we put 20 joules at the final, right, minus initial, obviously it will be 0. Now we take out the value as 20 joules. Now we take the minus W case. We have solved the left hand side, now we take the right hand side. And when we take right hand side, what we get is minus W is equal to minus delta K. Now what is that delta K? If you can recall, we just talked about the work energy theorem. Delta K means what? Delta K means the change in kinetic energy from initial to final stage. So we put this will be 0 because the change in kinetic energy at final stage, kinetic energy will lose out because the ball has reached the height, but initial energy will be there because it has been thrown, that will be 20 joules. Doing algebra, this at the final stage there is no kinetic energy. What we get, minus minus, it becomes plus, so it equals to 20 joules. So what do we finally arrive? We got that delta P equals to minus W. Both of these have got value of 20 joules, and this minus sign actually shows that gravitational potential energy has to be negative. So we have seen a basic definition, we have seen a kind of a derivation of the formula, and now we have illustrated with an example that yes, gravitational potential energy is negative. So in this video we saw and cleared up the concepts of gravitational potential and gravitational potential energy. Remember, both of them are not the same. One is unit mass and one it does not include unit mass. And in the next video I will try to clear up some more concepts on gravitation, gravity, all those things which comes in the classical mechanics. So this is the video which shows how these things are different and how we can derive that. So thank you for watching, I would say, this video, because I was trying to make this video so that I can improve on the earlier one. Please subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. You can email me for any issues or further discussion at this email ID. I also have got an exclusive channel for general theory of relativity in YouTube, and you can also follow me on my Instagram, Facebook and LinkedIn pages. Thank you for watching this video. I will wait for your comments, and I am coming up with more such interesting video. Till then, goodbye.